University of São Paulo, USP, and prior to that, she did her PhD in the joint program between Denmark and University of Paul Sabatier in Toulouse. And after that, she was also a postdoc in São Paulo. And very soon, next year, she will be our new colleague here at IMPA as a researcher here at IMPA. So her domain of research is mainly dynamical system and particularly complex dynamics. And today she will talk about the Mandelbrot set and its satellite copies. Okay, thank you, Luna.
Thank you very much. It's a great honor being here, telling you about my research. And I'm going to tell you about the Mandelbrot set and its satellite copies. We are interested in the dynamics of quadratic polynomials acting on the Riemann sphere. The Riemann sphere is the compactification of the complex plane plus infinity, and we consider a quadratic polynomial acting on it. For any polynomial, actually, acting on the Riemann sphere, infinity is a fixed point. Because if you are iterating, in this case, we are interested in quadratic polynomials. The quadratic family is the family PC of zeta, zeta squared plus c. And we are iterating this map for every value of the Riemann sphere. And, well, infinity is fixed, and it has a set of points attracting by him. And it's easy to see, because if you are a point very, 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 very big, when you square it, the modulus becomes even bigger. And when you square it, it becomes even bigger, and it becomes even bigger, and it becomes even bigger. And it gets attracted to infinity. So the basing of attraction of infinity is called AC of infinity. And in this setting, we can define the field in Julia set for a quadratic polynomial to be the set of points with bounded orbit. So we have our Riemann sphere. We consider the family, well, PC of zeta, zeta squared plus c. Acting on our Riemann sphere, we have infinity fixed, which has a basing of attraction. And we are interested on the field in Julia set, which is the set of points with bounded orbit. Okay, C is the field in Julia set for P C of zeta, zeta squared plus C. Okay. Here I put some examples. This is my favorite because it's very easy to draw. Is the field in Julia set of the map zeta goes to zeta squared. 0, it's a fixed point, and it's attracting. You can see that if you have a point with modulus very, very, very small, a complex point with modulus very small, take, I don't know, 1/2, squared becomes 1/4. It becomes closer to 0. Squared, 1/16. And squared, it's even smaller, and it becomes even smaller. So in this case, we have, okay, P C of zeta is zeta squared, 0. This is C. Well, infinity is there. 0 is attracting, is actually super attracting. Well, you can see that the unit circle is also invariant, and the unit disk is the set of points that do not go to infinity. It's the field in Julia set. K of 0. And we define the Julia set as the boundary, the common boundary between the basing of attraction of infinity and the field in Julia set. Here I drew several field in Julia set for several value of C. Here you see for C equals 0. Here you see for C equal 1/4. And here it's 1/4, C is equal 1/4 plus epsilon. And, well, here are other parameters. The first thing that one notices is that these sets are connected and these sets are not. We define in this setting the Mandelbrot set, which is this object we are very, very interested in, as the set of parameters C for which the field in Julia set is connected. So the Mandelbrot set, this guy, is a set of parameters. For each C, for each parameter, we have a dynamical system associated, which is zeta squared plus C. C equals 0, which is the parameter associated to this guy, lives here. C equal 1/4, which is the one associated to this guy, lives here. He lives here, and he lives here. And in the next slide, I will explain you a bit better of this set. So, as I said, we are interested in quadratic polynomial, zeta squared plus C, and we have each quadratic polynomial has two finite fixed points. Infinity is fixed, attracting, and then you have two finite points. We call one alpha and the other one beta. The Mandelbrot set, well, the beta fixed point is always a repelling fixed point, but at this point, where it collides with the alpha fixed point and they become parabolic. In the other case, it's always, always repelling, so it's somehow boring. So the one that does things is the alpha fixed point, and it's the point we are very much interested in. This point is attracting for every parameter here. In this, this is the main hyperbolic component of the Mandelbrot set, and for every parameter there, the alpha fixed point is attracting. And we are very much interested to figure out what happens when we move between this component and the other ones attached to it with the other numbers. And I'll try to show you. So, if I take 0, we saw before the field in Julia set of the map zeta square, it's the unit disk. This is K of 0. 0 is super attracting. Is my alpha fixed point. And my beta fixed point, let me get colors. And my beta fixed point is at 1, is repelling. And here, there is a period 2 orbit, which is repelling. Moving the parameter in this direction, we get that this period 2 orbit gets closer to my alpha fixed point. So if we are, blue wasn't the best color, I remember. If we get C here, well, let's take it here. We have that K of C is going to look like something like that. And getting closer to this point, this orbit gets closer to the alpha fixed point, till that at this point, the point in which these two components touch, the period 2 orbit merges with the alpha fixed point, and they become a parabolic fixed point. We'll see here, C hatching, and this is the Phil and Julia set of K, C hatching. Here we have the period 2 orbit that collapsed with the alpha fixed point and became a parabolic fixed point. Then, if I keep moving in this direction, what happens? Huh? Yeah, the thing is that then you get all the pre-images and then you get infinitely many components here attached. When these two things collapse together, you don't just get something like this, which is the thing that you would expect. You also get all the pre-images attached back. And if you keep going in this direction, what happens? My alpha fixed point becomes repelling, and well, the alpha fixed point and the periodic point and the periodic cycle separate again. The alpha fixed point becomes repelling, and the orbit becomes attracting. Let's put here C twiddle, and here we have these are attracting and this is repelling, alpha. Okay, this happens in any direction you see. In each of these balls, there is here, if there is a tree, it means that there is an attracting cycle of period 3. And what happened is that going in this direction, the alpha fixed point merged with repelling cycle of period 3. Here they become parabolic. Here the alpha fixed point becomes repelling, and the orbit becomes attracting. And here you collapse with a period 5 orbit, with a period 4, and blah, 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 blah. Okay? So, at the root points are the points in which one component is attached to the other. So this pa, 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 you get a parabolic fixed point with multiplier. The multiplier is the derivative at the point being exponential of 2 pi I p over q, where p over q is important because it's the combinatoric of the orbit. Q is the period, and p tells you how you go around, basically. Okay, so we are interested in this guy, the Mandelbrot set, and the first thing that you start looking when you look at the Mandelbrot set is that zooming here and there, you kind of see copies of the Mandelbrot set inside the Mandelbrot set. If we do a zoom here, we see this. And this really looks like the whole thing just without this cusp, just smooth, right? Then we can zoom again. We can look here, and then we will see this picture, which really looks like the whole guy. And you can start wondering what's going on. Are these actually copies of the Mandelbrot set? They are, And their existence, their presence in the Mandelbrot set, and in a lot of other parameter spaces, actually, is explained by the theory of polynomial-like mappings, which was developed by Douadier-Hubbard in 1985. So what is a polynomial-like mapping? These are going to be very important for the purpose of the talk. Well, a polynomial-like mapping, as the name may suggest, it's an object that behaves as a polynomial. Now, how does a polynomial behave? Well, we saw that if we have a polynomial acting on the Riemann sphere, we have that infinity is fixed and attracting, and the field in Julia set is defined as the set of points that do not go to infinity. So if I take a neighborhood of my field in Julia set, let me do it here because it's easier. And I look the preimage of this neighborhood under my polynomial, I get another disk which is compactly contained inside, right? Why? Because the dynamics, because the points are all going to infinity. They go pop, 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 pop. And your polynomial maps the smallest disk, call it U prime, into the biggest disk, call it U, properly holomorphically with some degree. P. So your polynomial about your field in Julia set is expanding. It does. A polynomial-like mapping is an object that encodes these dynamics. So it's something that does this. Formally is a triple. Here. Formally is a triple F U prime U, where U prime and U are topological disks. U prime is compactly contained into U. So, and F is a proper holomorphic maps that maps U prime into U with some degree D. And why am I telling you about these guys? Because Douadier and Hubbard proved that if you have a degree D polynomial, and then you define the field in Julia set for these guys, I forgot, as the set of points that never go away. For polynomials, it's the set of points that never go to infinity. Here, well, you don't have infinity. You have a local object. So it's the set of points that never leave U prime. This is KF. And why these guys are important? Because Douadier and Hubbard proved that if you have a degree D polynomial-like mapping, this is conjugate quasi-conformally, and actually conformally almost everywhere on the field in Julia set, to a polynomial of the same degree. So if I have an object behaving like this, I know that locally I am a polynomial. And the dynamics of the polynomials is the easiest dynamics you can find in complex dynamics. And here is every polynomial restricts to a polynomial-like mapping in a neighborhood of the field in Julia set, because it does. It's the model. But there are a lot of other examples. For example, let's look at this guy. This is the field in Julia set of zeta squared plus C, where C lives here. So what happened there? I have an attracting cycle of period 3, which is here, here, and here. And here, attached here, you see all the preimages of these components. This is mapped to this one, 2 to 1. This is mapped to this one. This is mapped to this one. And here are all the preimages attached. Okay. And this component is mapped to itself at the third iterate. The third iterate of a polynomial of degree 2 is a polynomial of degree 8. But if we restrict on this year, this guy is called the Duody Hubbard, the Duody rabbit for some reason. And this is 1 year of the rabbit. I don't know if this is. But if we restrict our attention just to this year, we see that the map sends the third iterate of my polynomial sends this year to itself. And here I have attracting, here is my attracting cycle. Here I have the basing of attraction of infinity. All these points are going to infinity eventually. So if I take a neighborhood of this year, which do not contain these other 2 points attracting, and you look at the pre-image is going to be compactly contained inside. And your polynomial sends one to the other properly holomorphically with degree 2. And this is a degree 2 polynomial-like restriction of a degree 8 polynomial. And this is the guy which is conjugate to him, because this guy is the center. You look what your critical point does, and this is the guy, believe me. But why am I telling you about this? Because this is strong, and Duody Hubbard also proved that under some conditions which are completely reasonable, there exists a homomorphism between connectedness locus of family of polynomial-like maps. What am I speaking about? This guy lives here, right? This is my guy. If I move a little bit here around, the dynamics do not change that much. Here I have, for everybody here inside, my periodic orbit is attracting. For everybody here inside, I can take a polynomial-like restriction of this guy. And for everybody here inside, there is a degree 2 polynomial, which is equivalent to him. And this degree 2 polynomial is a degree polynomial which has an attracting point. The polynomial with an attracting point lives here. And Duody Hubbard proved that actually you can find a homeomorphism that sends you all this thing to the whole Mandelbrot. Sending this component to the main hyperbolic component, this one to this one, and so on. So you can work with families of polynomial-like mappings and look in the set of parameters for which your Fielding-Julia set is connected, and under reasonable conditions, this map is a homeomorphism. So what you see here is actually a homeomorphic copy of this guy here. And this homeomorphism is dynamical. What does it mean? It means that if I send this point to this point is him. This is the Field-Julia set of him. And this point is him. This guy, locally around this part, it's conjugate. It has the same dynamics of this one. If you move a bit, if you go here, you see that you will find this Field-Julia set. And you see that inside, you will see a lot of copy of this guy, right? You see, pa, 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 pa. Why? Because this has a polynomial-like restriction conjugate to this guy. If I move here, I find this guy, which looks like a lot of these. And actually, he is conjugate. And very importantly, if I go to the root, I will find this guy, which looks like a lot of, these are called cauliflowers. We have a lot of name in complex dynamics for some reason. This is the Duody Hubbard. This is the basilica. And this is the cauliflower. And you will see a lot of cauliflowers here inside. So Duody and Hubbard in 1985 proved that these that are called primitive copies of the Mandelbrot set are homeomorphic to the whole Mandelbrot set. And the homomorphism is dynamic. Every point is equivalent to the other guy. Now, Lubitsch came in 1909 proving that this homomorphism is quasi-conformal. Well, after you have an homomorphism, you would like to know something about shapes, right? And it was already observed that this homomorphism couldn't be a diffeomorphism because the multiplier are not respected, and so it wouldn't work. And then it was something like, okay, what can we hope for? And we hoped for quasi-conformality, and it worked. What is a quasi-conformal map? Well, a conformal map is a map that respects angles, right? A quasi-conformal map is a map that is quasi-conformal. So it doesn't respect the angles, but it doesn't distorts, yeah, whatever, the angles that much. Technically, it's a map that is differentiable almost, in the real sense, at almost every point, and sends infinite circles to the best thing you can send it if it is not a circle, an infinite ellipsis. So a quasi-conformal map sends circles to ellipses such that the ratio between the major and the minor axis is bounded. If this ratio is 1, then your map is conformal. This is the Weil lemma. But in other case, you want this ratio to be bounded. You don't want the ellipsis to collapse. Okay? Duody and Hubbard, in this super cool paper, Polynomial-like Mapping of 85, proved that the satellite copies, okay, sorry, I forgot to say. The copies of the Mandelbrot set can come with the cusp or without the cusp. With the cusp are primitive, without the cusp are called satellite, and are the ones we are interested in. I'm sorry, I'm nervous. So, the primitive copies were completely solved by Lubitsch. Everything is homomorphic. The copy is homomorphic to the Mandelbrot set, and the shape is as similar as we can hope for. They are quasi-conformally homomorphic. The satellite copies are very annoying. Why? Because of the root. And Duody Hubbard proved, still in 85, that they are homeomorphic to the Mandelbrot set except at the root. What's the problem of the root? Well, we saw the problem going in this direction. Well, in this direction. Now we look at the problem in the opposite direction, which is here is the field in Julia set of the center of the period 3 components. I know that everything is there, but I will draw again here. So here we have my Duody Hubbard, IMPA, my Duody rabbit, which is very thin and thick. And I can take my polynomial-like mapping restriction. Then, the more I get closer to the root, the more this period 3 cycle get closer and closer and closer to the alpha fixed point. And what you see is something like this. I can still take a polynomial-like restriction, but I have less space. Because if I take these points in, here the preimage wouldn't be compactly contained, because I will have an attracting direction. When I get till the root, this cycle collapsed with my alpha fixed point. And you say that the Duadi rabbit became fat because it looks fatter. So here you have the attracting direction of my parabolic point. So if I take a neighborhood of this fat here, and I look the preimage under the third iterate, on this side, I have the basing of attraction on infinity, so I'm happy. But in this side, I have the basing of attraction of my parabolic point. So the preimage is farther away. So it does bloop and bloop. And the preimage is not compactly contained into the image anymore. This is not a polynomial-like mapping. Sorry for the technicality, but this is very, 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 very annoying. I had to write a PhD thesis for this problem. Because here, all the theory breaks down. You can take polynomial-like mappings, so you can't say that these guys are conjugate to this one, even though you have a basing of attraction, parabolic here. OK. Then Lubitsch came in the same paper where he proved the quasi-conformality of the primitive copy to the whole Mandelbrot set. He proved that this homeomorphism, the Duadi-Hubbard constructing that you can do from the satellite copy away from any neighborhood of the root. Because, I mean, the problem is this guy. It's the moment in which all the cycle coincide with my alpha fixed point. All the other points are fine. You can take your polynomial-like restriction. So they proved that you can't define the homeomorphism between this guy away from any neighborhood of the root till this one, and this homeomorphism, Lubitsch proved that is quasi-conformal. Then Isiski in 2000 proved that this homeomorphism can actually be extended to the root, but not in a dynamical way. Why? Because this guy is not a polynomial-like mapping. So the question that remained is that are the satellite copies quasi-conformally homeomorphic to each other? Why this is the question? Well, the point is that the satellite copy doesn't have a cusp, so for sure cannot be quasi-conformally homeomorphic to the whole Mandelbrot set, because we cannot straight a cusp quasi-conformally. No way. But all of these little balls have no cusp, have a smooth boundary. So maybe they are all looking like they have a common model. So what am I saying? I'm saying that, I mean, you consider the homeomorphism between the whole satellite copy to the Mandelbrot set, the homeomorphism between the other satellite copy to the Mandelbrot set, and you compose them. And you know that this thing is a homeomorphism, and that it is quasi-conformal everywhere but neighborhoods of the root. And so you wonder, can I extend it quasi-conformally to the root? This thing never been conjectured formally, but it was expecting to be true. Because if you take the logistic Mandelbrot set I will show you later, which is the double covering of this set, it looks like two balls like that. This one attached to the other one. I'll show you later. But actually, Lubitsch, in the paper where he proves the quasi-conformality of the satellite copies to the whole Mandelbrot set and the the satellite out of the neighborhood of the root to the Mandelbrot set and the primitive quasi-conformal to the Mandelbrot set, says that presumably the whole satellite set is quasi-conformal equivalent to the 1/2 of the Mandelbrots of this family, the logistic Mandelbrot set I will show you later. But why is important? Because if they are all QC to this guy, it means that they are all QC to each other. So this was the feeling that people had. And this feeling became stronger when I did my PhD thesis. Because in my PhD thesis, I was dealing with the satellite roots. What you can realize is that if you look the root of the period 3 component, you see this picture. And if you take is the duad rabbit with 2 ears. And if you take a restriction around 1 ear, the pre-image is contained on this side and thus blue on this side. If you take the root of the period 4 component, you have the same picture, just you have 3 ears instead of 2. And if you take a restriction of a neighborhood of 1 ear, the pre-image is nicely inside on this side, on the side of the basing of attraction of infinity, and then it goes away on the parabolic side, so blow, blow, blow. And this is the same you see at each satellite root. The only thing that changes is the number of blue, depending on how many ears this rabbit has. So something that you can do is constructing a model that behaves like these guys. I call it parabolic-like mapping, and you can write a theory with parallels, the one of polynomial-like mappings, and has as a consequence that on a neighborhood of the ear, well, pinched neighborhood of the ear on this side, any 2 satellite roots of any 2 satellite copies have restrictions that are conjugate, quasi-conformally. What I'm saying that this guy here behaves exactly as this guy here. Locally, they have the same model. So you start thinking, peraí, we have, spoiler. We have this map that is quasi-conform, is a homomorphism between this and this one, quasi-conformal everywhere but a neighborhood of the root. And the root have restriction quasi-conformally homeomorphic. This map is quasi-conformal, but it's not. We were trying to prove that it was quasi-conformal, actually, and we were something like, yeah, the conditions will be this and this and blah, 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 blah. And we realized that if the period is different, then your map cannot extend quasi-conformally to any neighborhood of the root. I just want to give an idea of the proof. I will give a geometric interpretation instead because I don't want to be technical. But the idea, which is not how, the idea of the proof is not how we got to the proof, because I mean, we were trying to prove the opposite, of course. But yeah, it's the easy way of explaining it, is that, well, we say that a K-quasi-conformal map is a homeomorphic orientation preserving homeo, which are differentiable almost everywhere, and it has differential at almost every point, which maps infinite circles, assume this is a circle, to infinite ellipses. And your map is K quasi-conformal if the ratio between the major to the minor axis is bounded by K. you want to prove that something is not quasi-conformal, you need to send decay the bounds of your dilatation to infinity. And the way we did it is finding a lower bound in dynamical plane between the conjugacy between two correspondence family of polynomial-like mapping, then doing a holomorphic motion argument in order to pass it to the parameter plane, and there sending the bound to infinity. The strategy of proving what you want to prove in dynamical plane and then do a holomorphic motion for passing to parameter plane, it's pretty standard in holomorphic dynamics. Duadi was saying plow, plow in dynamical plane and harvest in parameter space. But yeah, I don't want to give the proof is technical. But no, okay. I didn't expect the resolution like this. I wanted to give the geometric interpretation. I'm not sure it's very visible. Well, more or less. So we were looking about the map between satellite copies of 1/2 of this satellite copy and this satellite copy. We know that the map is quasi-conformal everywhere but a neighborhood of the root, and we want to give an intuition of why it cannot extend quasi-conformally to the root. So here you see a zoom of this part. And I don't know if it is visible, but I mean, well, attached to this guy, there are all these little balls, right? And they shrink going here. And here you see the zoom. And attached to the balls, there are decorations. And things start spiraling in these decorations. And here is a zoom of this guy, more or less here. And here, this one is a zoom of this part. You see that here, this picture is not very good, I'm sorry. But I mean, a zoom of this is this guy. And a zoom of this is this guy. And you see spirals in both cases. These spirals are very, 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 very close to the root. I mean, those spirals live here and here, not the other side. They are very, very, very close to the root. And if my homomorphism between one copy and the other had a quasi-conformal extension, we should be able to map this spiral quasi-conformally to the other one. This is not gonna happen. Why? Because, morally, Tanley proved that at these points, these are called the center of the spirals, are called the Mizurevich parameters. The Mandelbrot set is asymptotically self-similar and and it follows asymptotically the logarithmic spiral e to the tau lambda, where lambda is lambda to the q. E alla lambda is lambda to the q. And q is the period. This q is very important. So, and this spiral has step ratio of self-similarity e to the lambda to the q. So basically, if you were sending one spiral to the other quasi-conformally, let's say that you send one spiral to the other, then you do a zoom, and you see the same picture. And you should send it to the same picture you see. But these zooms are different, because these spirals spiral at different speeds. So you have a picture here, you send it here, then you zoom it, pa, and you zoom it here, but I mean the ratio is different, and you need to map one to the other. Okay, you can do it. Then you zoom in again, pa and pa. The ratio is even more different, and you can do it. But if you go to the limit, these ratios are too different, and it's not working. The problem being that these ratios of similarity are different. And this is the moral reason why you can't extend quasi-conformally the map in a neighborhood of the root. Thank you very much.